good afternoon. I am extremely happy to introduce to you a very distinguished speaker, Professor S.K.Pandey, presently Vice Chancellor of Raipur University. It's a pleasure for many reasons, because Professor Pandey is a very old friend. That is the greatest privilege and pleasure. Very old friend. We have been friends ever since our university days, when we were studying in our master's program. And then subsequently thereafter we continued to be in touch and good friends. Professor Pandey, after completing his master's program, went for his doctoral work from TIFR, which you know is one of the premier institutions in the country. And then after that he joined as a faculty at Raipur University, so that was another occasion when we continued to meet. Raipur happens to be my in-laws' place, so I would always go back to Raipur and meet Professor Pandey. And then I have been seeing him working and developing the department. An extremely gifted teacher, let me tell you. Extremely gifted teacher. A very popular, highly respected teacher. And an eminent researcher, internationally known for his work in astrophysics. He has been, instrumental in transforming Raipur University during his tenure as the Vice Chancellor of Raipur University, bringing programs that all of us have heard about, but never thought that these programs can be brought to university. Highly sophisticated instrumentation facilities for research, analytical facilities, as advanced centers, and many other levels. So he has a very, very illustrious career, both as an academician as well as the Vice Chancellor. He is now having a second term as the Vice Chancellor in the same university. So I am extremely happy and proud to have him here in this university. He has also been the Vice President of the Astrophysics Association. Yeah. Has been continuously associated with the IUCA program as an extremely modern laboratory at Raipur. Today, Professor Pandey would be sharing with you about our universe. That is extremely important. And I'm indeed very, very happy and to invite him, Professor Pandey, here to deliver his talk. Professor Pandey.
Good afternoon, everyone.
Good afternoon, sir.
I'm extremely privileged to be with you today in this university. It is headed by my senior colleague, Professor Pandey. I have been following him from Bhopal to Gwalior, now to NEET University. I happen to be in Delhi for some other work. and I was very curious to visit the university, which the name I had known, not as a university, but as an institution name. So I spoke to Professor Pandey and at his invitation I am here, and I don't know whether I can do justice to whatever he said. Yes, one thing is very true, that I love to interact with young minds, because that provides me fresh air in my thinking process, with the hope that at this age I too can do something, if not for me, for the youth of our country. So, well, my area is astronomy. And astronomy, as you all know, how many of you have ever attended a program called Inspire in your school days? No? None of you? That's great. Very few. This is a program which we have been running our campus at Raipur for the last 3 years. And that is where we get the opportunity to talk to 10 plus bright students with the hope, and where we invite top scientists drawn from various top institutes within and out, as well as outside in principle, experts in basic sciences like physics, chemistry, mathematics, life sciences. And the sole objective is to attract them to remain in the basic, in the stream of basic sciences. That doesn't mean that we prohibit them to join courses that you are attending, but primarily that wherever you are, you should have the basic grasp of basic science if you want to flourish, if you want that you can make a career out of the course that you are following. And that is very successful. So during that course, I get the opportunity to interact with young minds at my university as well as elsewhere. And often I give this kind of lecture to them, so without much changes, I have borrowed the same kind of stuff for you. I do not know how many of you are aware of astronomy, or read about books on astronomy, about the universe, its beginning. But perhaps, as and when some new things, news breaks, right? This world will collapse, right? Or there is a storm of the sun and it's approaching us, solar tsunami. Then we do get frightened. But my young friends, that is where you need to know our surroundings. The universe, that religion. The universe, we are very part of it. So let me begin the picture that you saw, that you see here. You know what it is?
Solar flares.
Solar flares. And quite recent one. So you see, my topic is our universe as we know now. I didn't say as we know today, right? Because things do not change that fast. But it does change. It is changing every second. Right? The scales that we study in astronomy is significantly different from what you do in your laboratory or classroom. Right? Time scales, the length scale, the masses, entirely different. But that is where, and the way we carry out our observations, we do not do experiments, we carry out observations. We see as they are up in the sky. And the only source of information is that the light that we receive from them. Right? I don't know how many of you, how much time the light takes from the sun to reach us.
8 minutes.
That is our star. But think of stars twinkling in the night. The nearest star, which is part of our own galaxy called Milky Way. You know how far away the nearest star is? 4.2 light years. And you know what a light year means. In the same spirit, if you keep on asking the same question again and again, and if you ask me, what is the farthest object that we have seen, quote unquote, observed so far? I will say it is several mega light years. Right? And that is where we need to learn how big is our whole universe? How did it begin? What would be our role? Right? So I would like to share some of the things with you to excite your interest, satisfy your queries if possible, and take you to journey of the cosmos to some extent. You know these two faces. I don't have to tell them who they are. They did wonderful work in astronomy. And that's not both of them. One did in what you all know is Raman spectroscopy now, Raman effect. The other one is known for his work in astrophysics, Chandrasekhar mass limit. So I am deliberately doing this, putting this before you. They are the ones who received Nobel Prize in Physics. They are the ones, they are our pride. They are the ones that we should take an example. That is where we need to reach. So that is the spirit in which I am giving this lecture. Well, as always happens, whatever is being taught in your school or in classroom elsewhere, the first question that you should ask, you ought to ask, is why should I do this? Right? And something that you can read is the question that has been there for ages. The answer which were there since then, but still we ask that question because that takes you much further away, right? See, this reminds me a question which was asked to Edmund Hillary in Norway after they come down, after climbing the Everest. As usual, the media person asked me, why Everest? You know what was the answer? Yes? Because it is there. So that is the curiosity. You need to understand your environment. You need to know your neighbor. You need to know your town. You need to know your university. Even though, because you are part of it. And if you continue this chain of events, believe me, my friends, if you do this, if you start asking questions, who am I? This will take you, every one of us, whether he or she is asking question or not, to the very beginning of the universe. So that is the beauty of the study of astronomy. Right? You all always talk about Vasudhaiva Kutumbakam, isn't it? Now, I am providing you another opportunity to even expand that horizon. It's all one. Because at some time in the past, everything that we see, or which would be seen in years to come, were part of the very universe, our own universe. Right? We talk about biodiversity. Right? We talk about coexistence. The very fact that everything came out of the same matter, right? So whether you talk about living things, non-living things, biological things, rivers, mountains, right? Human life, different forms of life, the striking similarities and dissimilarities that you see, this part of diversity, natural diversity of nature that has provided to us in the universe. Right? Have you read this? What Kepler said? So don't worry if someone asks you, even though it's not part of your syllabus, still why are you being taught astronomy course? Right. Yes. There's a question which Albert Einstein asked him to himself. You know what he did? He was known for the theory that he founded for photoelectric effect. Then came the special theory of relativity. Then came the general theory of relativity, which is essentially theory of gravitation. And it has enormous application. Was applied to the universe at large, what we call as cosmology. But the basic question, that he asked to himself, I want to know how God created this universe. I am not interested in this or that phenomenon. I want to know his thought, the rest are all details. So that gives a very important message for all of us, especially for the young minds from whom we expect a lot. What is important is your thought process, vision. How do you look at the things? That is a materialistic view or something very objective. So that is the objective with which Albert Einstein studies the universe. He proposed theories. Somehow he thought this universe is still state I'll talk about later. But let us now see how do you start looking at our universe. Galileo showed us the way. No? We celebrated a few years back 400 years of telescope. You see, he first demonstrated in 1609 AD by pointing out a very small, very tiny telescope, slightly bigger than our eye lens. With that, he discovered craters on the moon, hills on the moon, sunspots, right? Moons of the Jupiter, and many more stuff. So that is the beginning. And what is the thrust? Starting from that day, look at the curiosity of the human being. Bigger and bigger and bigger telescope. And you should ask yourself, why? Why do you need bigger telescope? Yes? Can someone, yes?
So to look more deeper into this place.
Yes?
Because it is there.
Because it is there. But you need to see, the question is, why do you need bigger telescope?
To discover more, to have a greater resolution of the astronomical objects.
Yes.
Have a clear clarity.
But what is harm if you do it with a small telescope? Smaller
Be
one.
able to look at a greater depth of what is going on the planet or anything. Greater detail.
Okay. So in a sense, most of the answers are correct. Right? But it has deeper meaning in it. Ideally, given a small telescope like you would like to have in your campus, let us say 6-inch telescope, slightly bigger than what Galileo used. So ideally, if you put a detector at the back end, right, a CCD camera or a photometer, which can not only see with eye, you can see it, but you cannot retain it. Right? But if you put a photographic plate or modern technology, CCD cameras, photometers, solid state photometers, cameras you can keep on recording for ideally for hours together, but that hardly happens. Right? And if something goes wrong, you are likely to lose the entire data. The choice is you make bigger and bigger telescope and have shorter and shorter exposures, isn't it? So that is the spirit, because you do not have infinite time, right? With finite time, in what way I can understand the universe in the best possible way, most detailed manner. So that has led to development of bigger and bigger telescope, and the current functional telescope that we have in the world is a twin telescope. And again, why do you need twin telescope? I don't have to answer this. You all know it. Why you have given two eyes? Same spirit, right? So these are the twin telescopes that we have in Mauna Kea, the mountain which is supposed to be the heaven for astronomers in the US. But this quest for probing universe deeper and deeper, fainter and fainter, further and further objects, now has led to the development of even bigger telescope. Now we are talking about 30-meter aperture telescopes. Large telescope, very large telescope, very, very large telescope. We can put in some more new nomenclature. So our country is also involved in one of the mega projects called TMT, 30-meter telescope. You will be participating by paying money and constructing something for the big telescope. This one in South Africa is a 10-meter telescope, and we have access to this telescope as well. What is called buying telescope time, right? You don't have to erect necessarily telescope on your homeland. You can buy telescope time. So this is functional. Yes. Now before I dwell upon the space telescope, this gives you a nice overview of the complete spectrum that you have on the top. Here, as you can see, and you notice that color, small visible window. That is what our eyes can access to. But look at the entire spectrum which is accessible to us, but not from ground. Only part which is accessible from ground to us is the one which we normally call telescope, but we mean optical telescope, is this, or radio telescope. But in principle, we can talk about telescope in every small window or band of the spectrum. So you must have either read or seen telescopes like infrared telescope, X-ray telescope, UV telescope, like this. But they cannot be put on the ground. Why? Because there is a blanket called our atmosphere, which absorbs most of this UV, X-rays, and even far infrared. And that is why we are here. Right? If there is no atmosphere, you will all die. Isn't it? But the same atmosphere prevents us to have a look at things. This has been doing wonders since 1990. Right? Still in Norway. And most of the wonderful things that you might have read or seen or which appears in newspaper, credit goes to, it's not a big telescope, it doesn't carry a big telescope, just 2-meter class telescope. But simply because it's away from the outside atmosphere. So blurring which atmosphere creates is taken care of. We have a wonderful view. And it is orbiting and continuously monitoring the same objects for months together. That is the basic objective. Right? So I am not going to show some pictures taken by this. The other telescopes orbiting in the space, and then even many more, some of them. So infrared, Is the gamma rays, Chandra, like this. Yes. So here I'll ask a question. I think I do not want that you should get into unnecessary details, which you all know. Right? So if you tell me you know about solar system, there's all images. I'll just skip this part. Right? Yes? Shall I skip this part? Okay, great. Yes. I'll ask you a question. Why is moon important for us? What if there are no moon? Yes? Yes? What if there is no moon?
No
Yes?
time.
Very good. Anything else? No? Okay. But see, I'm for one reason I'm precisely urging for a moment here. See, the moon has been a center for attraction, right? In Vedic times also, right? You know why? You remember recently we sent a mission to Chandrayaan and we discovered water molecules, right? But one important thing, you know, we have ISRO, institute like ISRO, artificial satellites. Who paved the way for having idea of artificial satellites? Well, we could have done it, we could have thought it over. But moon essentially, the very fact there is something which is orbiting our own Earth, in a sense guided us how to construct a new moon which can do our job at our will, at our control. Right? That's what all the satellites are doing, including the recently launched satellite of ISRO few days back. Okay, this is a comment. Now, I don't know how many of you, I think most of you know what is source of energy for the sun. Yes? Do you know it? Now, without going into much details, I'll ask you a query. Because I love to interact and get answers from you and modify wherever necessary. What do you think? The elements that you see distributed in our earth, within, outside, right? We are all carbon-based life form, isn't it? What do you think? Did the nature provide all these elements in a natural manner? Or there is a place where universe created first, but starting from hydrogen, these elements were synthesized somewhere in the cosmos? What is your opinion? If I ask you the common question that I often ask, we're all fond of gold, silver, diamond, isn't it? Who would not love to have diamond rings and diamond necklaces?
But they were part of the star. There is a theory that all these elements present were the part of the star. When the star glows up, like the iron, the gold, these particles have been made from that. Due to blast of this particular, like a star is especially has a iron, so made of iron, so that it blows it. So then all the elements due to gravity is the main part of the universe combined. So that's why we have all these elements.
Yes, he provides part of the answer. Any other clue? See, you gave me the answer, right? There's a nuclear reaction which has been going on within the sun. It is source of energy. What is that nuclear reaction? Fusion reaction. Thermonuclear fusion. And it doesn't go out of its own. We need to create right condition, and that unfortunately exists within the sun. And again, I'll take you to the good old days when finding a source of energy for stars like the sun in early 20s was a big problem. Eddington wrote a book, The Internal Constitution of Stars. He too was faced the same problem. Somehow he was convinced that stars like the sun, they are hot enough in their center to trigger the nuclear reaction that very firmly we know now. That you'll be surprised. See, I asked you, you knew it so well. But in good old days, the same kind of argument when it was put forward by Eddington, people did not agree to it. And that poor fellow was so frustrated. He said, not in his words, but I am putting it in my own words, those who do not believe that the sun center is not hot enough for processing the nuclear reactions, let them go and find a hotter place. So he was so desperate, and somehow he was proved right. Right? That is the kind of vision, ingenuity, proper thinking based on scientific thought is required. Right? And he was proved right, as I said. Now, not only is this the source of stars like the sun, but such nuclear reactions keep on occurring inside other stars, right? One after another. And that has this another thing that you all know. Yes, well, I think yes. So let me complete that story. Hydrogen to helium. What next after helium? Carbon 12. We are all carbon-based life, isn't it? Right? So carbon 12 was essentially cooked inside stars like the sun, not inside the sun, because sun is not massive enough for it to have very dense and very hot at the center for the synthesis of helium into carbon. You need a massive star, much more massive than the sun. But there are stars like those, more massive than the sun. So this is the diagram when people took data for a variety of stars that we see twinkling in the night sky. Right? Young persons like you spend nights after nights collecting data on stars, right? And that is what they created. It's called HR diagram. Loosely speaking, this is the horoscope of stars, right? Although we do not believe in astrology, but that's why I said loosely speaking, in the sense of prediction. If you tell me the position of an object, star, in this HR diagram, in principle, I can predict how it came to that place and what would be its future. That is what we call as evolution of star. So you can depict the evolution of stars ideally on the diagram known as Hertzsprung diagram, was created sometime in 1922. Right? And based on just two observed properties, luminosity and the temperature, are what the astronomers call a spectral index. Right? And our sun is somewhere here. Right? I don't know why. Yes. This is what we call as bell sequence stars. Again the question, why most of the stars are located on this bell sequence? Because all the stars which are located on bell sequence, they are burning hydrogen to helium. And that process among all the reactions has the largest time scale. Right? There are other burning processes, but their time scales are shorter. So, statistically, you find whenever for a large sample, you will try as our diagram, you will always discover this, that majority of the stars lie on this diagonal strip known as, and very simple physics which you have read in your schools, the Stephen-Boltzmann law, you can very easily figure out why we call stars located here as white dwarf. Why do you call stars located here as giants? Right? Why do you call blue, red? Right? So I'm not going to tell you, you can work it out yourself. Yes. Thus, roughly how stars evolve, starting from their birth. This I took from somewhere in the internet. So starting is here. From large chunk of clouds, primarily in the form of hydrogen, very less helium. So that's how it made the initial beginning. As someone rightly pointed out, gravitational is the only dominant force. Something happens, we don't know yet. We call it instability. It happens in our laboratory also. Otherwise, crystals would never grow. Isn't it? If you put a sodium chloride solution in the proper condition, crystal grows. The whole, say, liquid solution doesn't grow into single step. Right? Some seed has to be created. How does it happen? We give it a name by instability. Something happens, starts contracting, and so on. Yes, yes. So that is this on the left hand side is cycle which starts like sun would follow eventually, becoming a protostar which is likely to become star, then our star like the sun. Then once that source is exhausted, what will happen to the sun? Natural question that you ask, because there is our star. How long will the sun live? What is time scale for the sun? It's terrifying, right? If someone tells you that sun is going to die tomorrow, then you all be terrified, isn't it? No. Will you be terrified?
Yes, sir.
And therefore you ought to know how long will it live. When I wake up next morning, will the sun rise from the east? Right. And how long will it keep doing like this? That is the question. Yes?
5 million years more.
5
million years. 2 billion, sorry, it's billion.
Right. See, in astronomy, we worry about order of magnitude. Right. We do not worry about 1.2 or 2.3 billion years. Perfect. And I leave it to you as a home exercise to find out where did you get this number from. Right? But it does. Whatever it says, it has already lived around 5 billion years.
4.5.
To be precise, 4.5. And an equal time to live. It is evolving. Every second is evolving. Because it is burning hydrogen to helium. But I think several generations of ours would pass through before it says goodbye to us. But that day is certain. One day it will say goodbye to the universe. Right? Okay. But what about other stars? Massive stars. Because there are stars which are slightly less massive than the sun, and stars more massive than the sun. See, I did mention about going off, but the correct terminology which astronomers use is something else. I will show you in a minute. Massive stars. Initial process sounds similar. As it grows, things change. Things change because it doesn't, see, the nuclear burning process doesn't halt after hydrogen burning. It continues. Helium to carbon, carbon to oxygen, till what? He also gave iron. But I'll ask you a question, why iron?
So because it has the most stable nucleus.
Good. Very good. But why it is more stable?
Depends upon the number of nucleons.
It's binding. Let us use the physics terminology. Binding energy per nucleon is the highest. So if you draw binding energy per nucleon versus A, there is a peak. On either side, see, if you are fusing lighter into heavier, it is always accompanied by energy release. And same manner, fragmentation of heavier elements into stable nuclides will always be accompanied by release of energy. So that's what happens. But the question remains, where do you synthesize gold and iron, gold and silver?
Sir, it's because of the supernova.
Yes. Not because of supernova.
Sir, supernova explosions happened, and there's a theory that all the elements higher than iron are formed because of supernova explosions.
See, not because of supernova explosion. As I said, supernova, when the explosion takes place, more energetic particles are thrown out, and the envelope then has the right kind of condition where this thrown up higher nuclei can pick up additional nitrogen or proton and keep building the heavier element. Right? Now the basic question, where did we get it? So obviously we are not the first generation star. Our solar system was not born out of primarily hydrogen and helium. It already had traces of heavier element. That's why we see elements up to uranium. Isn't it? It's not a first generation star. So ideally first generation star should have signature of only hydrogen and helium. That's all. Right? And all heavier elements are essentially thrown during explosion, supernova explosion. And there is a very rigorous theory built up by our nuclear physicists, right from hydrogen synthesis, hydrogen to helium, and up to heaviest element, right? And it's a standard theory. People take it; it has been tested. So, gentlemen, now I'll talk about the end products. Here also. What are the end products of stars? So, stars have their own life, isn't it? Just like we do have. We are born, and the very fact that something happens, something exists, has a birth and it has a death. That is certain. It applies to stars also. But question is, what is the end product in case of stars? What is here? You all know. White dwarf. And if you happen to join physics at some stage as part of your career, you would know what is the cause of stability of white dwarf, for which Chandrasekhar won Nobel Prize. Isn't it? Even if we have not done it, we ought to understand what is so special contribution of Chandrasekhar, which earned him Nobel Prize and so much remuneration. You need to learn that. Right? Okay? Do you know some of you? Have you learned about degeneracy? Degeneracy pressure, degenerated electron? No, forget it. Don't worry. There is something which, even at that stage when there is no nuclear burning going on in the center, is something which prohibits further contraction and keep it in a stable state. That is called degeneracy pressure. Don't worry. Now, same thing you can ask, what happens to, what is the end product in supernova explosion? Is something left behind. Chandrasekhar gave a mass limit for this. How much is that?
1.4 times.
Sorry?
1.4.
3 to 4 times the size of sun.
No. I think you are just making a guess.
1.4.
Is such a beautiful theory, right, which Chandrasekhar did. And you can calculate it precisely. 1.4 solar mass. Exactly, and I am saying exactly means, see the mass limit comes in terms of fundamental constants like mass of proton, G, capital G, gravitational constant, mass of electron, speed of light, things like that. Pakka, there is no ambiguity, right? Now, what does it mean? That if the end product exceeds mass set by Chandrasekhar mass limit, you may ask, what happens then? Something happens, let us not go into details. But it is a perfect physics theory. See, there is an electron degeneration in case of white dwarf, which makes it a stable one. But next to electron degeneration is when the electrons, free electrons combine with proton to give you neutron, inverse beta dt. So you have a neutron matter. And that's how you give a name, neutron star. So primarily, it can be viewed as a giant nucleus with a mass number typically, can you guess? 10 to the power 52 or something like that. Its mass is typically, still we do not have the exact, the way Chandrasekhar did. If you ask me, what is that exact critical mass for a star to end as a neutron star? I'll say it's approximately to 1.8, depending upon what kind of assumption you make in formulating a theory. That is because we do not know yet what kind of, see, matter, what would be the conditions. That's very high temperature and high density. This question you may ask, when we say that it began with a Big Bang theory of the universe, what was there before? And what was the form of matter before it broke? So still we do not know how the matter behaves, high density and high temperature. So that is why there is ambiguity in framing the exact upper limit for masses of neutron star. But what is certain is there exists a mass limit. There is a limitation that we are unable to calculate it. But nature knows where to stop it. Right? That is how there is a next stage of end state. That is called black hole. So, such core, left out core, which exceeds the critical mass for it to become or end up as a neutron star, exceeds that mass, there is nothing to prevent from further collapse, keep on collapsing. But during this collapse, another dramatic thing happens which Albert Einstein has told us. Gravity becomes very strong. And then the time and space no longer remain isolated. You must have learned about the time cone. Right? So you can analyze this. So black hole means literally black hole. Nothing comes out of it. Alright? Because this gravitational pull has become so strong that anything that goes near its what is called event horizon, it is captured, it's lost forever. So that is roughly gives you nearly a picture of what is called life cycle of stars. Now this is what you can depict in your HR diagram. Yes.
So you said that whatever goes into the black hole is never found. Is it, does it get trapped or is it thrown away to a certain location?
No, it's not, it's a trap. It is a leftover. Whatever behind during the supernova explosion, it critically depends upon its mass. Whether it would end up as a neutron star, for which there exists a critical mass limit. Unfortunately, we have not been able to find that critical mass limit. But we have put an upper limit for that. And if that mass of that core exceeds that limit, there is nothing to prevent the further collapse. It becomes what we call as black hole. The question is, how do you know black hole? black hole has been there. Now, see what I am saying, even though it looks like a story, right, you will find me a storyteller, but it is a fact. Such objects do exist in nature. This is called planetary nebula. I am sorry. And the object in the center is eventually going to become a white dwarf. After the matter which has been spreading will ultimately mix up with what is called interstellar medium, space between two stars. That is the reason from where new stars are born. Right? The same thing happens from supernova explosion. The ejecta ultimately will, with the passage of time, will build up gradually in its volume and mass, and as contraction process begins due to onset of instability, now it will become a star of second or third generation. Yes, I talked about white dwarf. Someone should show me where is the white dwarf, isn't it? Right? And our own brightest star that we see in the night skies, Sirius, is a binary star. The one which you cannot see with naked eye turns out to be white dwarf. Right? This little one here. Right? So, astronomers are not merely storytellers. They are not merely in the process of formulating theories alone. Unless it is vindicated by observational evidence, it would remain in the domain of intellectual propriety. Yes?
So what if it's further away and not that small?
Sorry?
What if it's further away than the bigger star and not that small?
That is a star. But what bigger star?
No, I'm saying, what if the smaller one is like farther away and the same size?
This one you're talking about, right? This is this one?
Yeah.
See, this is the brightest star called Sirius, A-type star. But it's not a single star. It has a companion star. Now how do you know that there is a companion? Right? So again, it is gravity which tells you all the story. It is hidden behind. If you follow how the path of Sirius has been changing over the long period of time, you will see it's not a straight path, it undulates. From there you can calculate theoretically, right? What could be the other one? So there exists a neighbor star is certain, but other properties can be calculated from the theories of binary stars, which is well developed now. Right? Yes. This is something which would be those of you who would by their own, if they plan to study this. Yes.
So we all know that stars have this incredibly huge number of masses. Now, in this law of gravity, several many masses with the huge numbers should attract towards each other. So why do constellations and why do stars not move towards each other at a very rapid rate?
But see, why do you always think that only one of them is attractive? Both are attractive, isn't it? But see, the very fact that they are, see, suppose, think of a process during the course of formation of stars, right? Binary stars have been created, just like our own solar system. What you are asking is, why doesn't the moon fall on the earth? So I'll the same question. You know the answer. Right? Yes. So this, I think I have tried to answer you why there are heavier stars. So essentially stars are the furnaces. Right? So gold, diamond, silvers, my young friends, is not nature given. It's something created somewhere in the cosmos and distributed to us during the course of formation of solar system. and Earth has been fortunate enough to take its own share, which you all enjoy very favorably, right? So, one point where I can have a stop at this point, but if you are ready to listen to me, see, astronomy has no end. And that is the beauty which I enjoy. I always say, Hari Anand, Hari Katha Ananda. I can stop at any moment without being noticed. I can start at any point without putting a question. I could have very well started from galaxies, or right from other end, from the beginning. Yes, so either I can open to you all, can ask questions, and depending upon what you ask, I will show you some other slides, because it becomes too boring, isn't it? You will not utter a word, you are a first year student, right? But I know the mindset of young minds. It's too boring to listen to long lectures, right? I too like to have interaction with you. So, for a moment I'll start here, but I'm very happy to answer your queries related to other things of the universe. So, the story that I told is part of the story of the universe, right? Still, some other time. Yes?
Sir, recently I read an article about white holes being discovered.
Huh?
White holes.
Holes being discovered?
White holes. Like
yes, white holes.
Like black holes. What are those?
Where did you see? It has been there. White holes is just ulte of black hole, right? Just opposite piece. But so far, we do not have any evidence. You can see, basically we are trained physicists or mathematicians, right? You would like to know its evidence. But so far there is no evidence of white holes. But theoretically, yes, it's possible to have white holes. People also think that there is an anti-universe, just ulta of universe, right? And these two are connected by a wormhole, right? So there are so many speculations.
Sir,
yes?
we can't have white holes because we have learned that gravitational force is always attractive in nature.
Yes.
So how can it opposes anything like white hole? In
Yeah.
a black hole, everything is getting attracted because of the gravity.
They'll ask this question, what about supernova? Gravity could not prevent the ejection. See, depending upon which force is dominant, things would happen that way, isn't it? Right.
Sir, can you explain something about the ejections through the black hole?
Well, not the ejection, but people did try that. Is it possible to extract energy out of black holes? As a particle, while encircling, approaches what is called event horizon. And there is something called Penrose process. I cannot describe you in detail, but there is something called Penrose process which allows you to extract energy from black holes. So that is the only information I can give you.
When they have enough mass sucked inside it, they eject some kind of rays out of it.
That's what I'm saying. It's called Penrose process, right? Like
By itself.
huh?
By itself, not extracting. By itself.
That I don't think I would be able to answer. Not by itself, but there is some process called Penrose process. I cannot describe in detail, right? Which somehow allows. See, ideally a black hole prohibits to have any information about it because we have lost the time frame, right? So we lost complete information about it, and the only information that we can have is about. That's why we often say black holes have no hair. But then people thought, see, people like Penrose and Hawking process, Hawking Penrose, they somehow thought that it's possible to extract energy some way. But I'm sorry, I don't know able to describe that event to you.
Now one more query. What is a wormhole?
Wormhole is one which connects white hole. Well, actually, wormhole is one which connects universe to its ulta. Ideally, black hole to white hole. Yes. See, this is the concept of black holes. The geometry that you talk about on the top. This one. The light cone, and then how it bends onto itself, and what happens when it is exactly equal to C. Yes?
Yes, sir. So when a star becomes a black hole, so it's said that it becomes more stronger in gravity.
Yes.
So how does that happen? The mass is constant, because how can it gain more mass?
Oh, that's a very interesting question. That is because, see, there are situations where you can have a neighboring object, right? What is called closed binaries. See, I gave you example of Sirius and white dwarf. So obviously the other object, or which you are calling white dwarf, must have evolved over the time. So during the process of evolution, depending on its part, one of them can evolve first and become, let us say, neutron star or black hole, which has very large surface gravity. But the companion is still in the what is called main sequence phase. So this can keep accreting matter from the companion. And this is what exactly happens in closed binaries. And you can notice this in form of emission from the X-ray binary as a whole. Very difficult to separate the two. But you can notice that such binaries are strong emitters in X-rays or even ultraviolet. And if you can combine this with the optical observations, it is possible to formulate a theory and put at least an upper limit on the mass of that unidentified object. And that is how we have reached the conclusion whether this object is a massive black hole or a massive neutron star. Neutron star or black hole. Yes?
Sir, can you tell us anything about negative mass?
Negative mass. See, why do you think, tell me first, why did you think that there should be negative mass?
I heard that someone from Japan won a Nobel Prize for research in this.
See, material science, they talk about motion of electrons in a crystal lattice, right? And that is how the concept of negative mass arose. But that is not a true mass of the object. It is the effective mass, which may turn out to be negative depending upon the interaction that it sees as it moves around. Prof S.K.Pandey will be able to explain you better the concept of negative mass in material science, solid state physics, to be precise.
So what was the concept of time travel proposed by Einstein? It is said that if he was alive, he would have developed a time machine also.
He could have developed
A time machine.
time machine to do what?
He had a very fine research on time and space.
Well, that is true. He did a lot of work in his basic objective was I don't think he ever tried to develop or said that to develop a time machine. Right? What he said is unification of all the forces of nature. That was his thought process. He used to think that all the forces of nature, gravity, which is the weakest of all, nuclear force, the strongest of all, plus two more, electromagnetic and what is called weak force. So he somehow thought that all these forces should be unified into one single force. And that is what has already started happening with the unification of electromagnetic force and the weak force, for which Abdus Salam and Weinberg, they got Nobel Prize. But see, that unification, see, cannot take place energy that we are accustomed with. You need to go to very high energy. And that is how the early universe becomes very important. Yes. Yes, I think. So, any other question? Already, yes.
So my question is related to the time machine. and
BTech students.
I think, and it is,
Then I would tell me first of all, what do you really mean by time machine?
So that's what I'm saying. When I speak to you, there is some sort of energy release, right? Right? So when I speak to you, some sort of energy is going to your ear. So if we can capture that energy and go ahead with that, so we can see,
Oh, all that you want to see, what, for example, my lecture, even if you do not regard it, sometime in the future, someone can see, catch it up and see, look, gentlemen, S.K.Pandey delivered a lecture in such a such classroom so many years back.
My point is that we can, if we can create some something which can go ahead of that energy, then we can look back at that energy and then time machine is possible.
Right, you can frame your ideas and send it to my email address. I'll try to find out answers. This is all speculative, but I definitely encourage such speculative questions as well, but not necessarily I can provide you answer immediately. Right. Yes. Sorry, I didn't get it.
You have speculated that to extend the programming theory and the layers universe, it goes on particle to be elaborate more.
No. That was, I think you are confused. See, Higgs boson, the concept of Higgs boson arose because the standard model of particle physics, which we all know, requires this for completeness. What is the standard model of particle physics? 3 families of quarks, 6 quarks, 3 families of leptons, some filled quanta like photon, right? So that people thought is a complete structure that we have for the elementary particle physics. But the question that arose at that time, what is it which gives mass to a particle? Right? To which, about 50 years back, this old man who is still alive, he had proposed a mechanism called Higgs mechanism, which actually gives mass. Larger is the strength of interaction, more massive the emerging particle will become. So that was the concept. Right? So there is a Higgs field. Every field has its quanta. So he talked about Higgs field, quanta of which is Higgs boson, is a boson. But you need to identify such thing, and this can be done only at fairly high energy, typically mimicking the early phase of universe. And that is one of the objectives of Large Hadron Collider. And as far as I understand, I am not a particle physicist, nor do I claim to know the final details of the outcome, but they do have found it true for the Higgs boson. If that is discovered, not only the old man would get Nobel Prize, but our theory would be complete.